Welcome to 10.3, Day 1, Geometric Sequences and Series. The learning targets for this lesson is that you'll be able to find the nth terms and geometric means of a geometric sequence. And then the later learning target, that you'll be able to find the n terms of geometric series and the sums of infinite geometric series. We begin by defining a geometric sequence, and you should be familiar with this, or it will look familiar to you, because we actually dealt with these in 10.1. A geometric sequence is most closely related to exponential functions. So those problems where you had a common multiplier to get from one term to the next, that multiplier was the base of the exponential function, and some of you figured that out and wrote your rules. Well, for a geometric sequence, it has to have a common ratio, or a ratio between successive terms has to be common. It has to have a common or constant ratio between successive terms. We call that common ratio R. It's kind of like our common difference D. Our common difference D in 10.2 was the slope of the equation. Our common difference R is going to be our base of the exponential function. Determining the common ratio and finding the next three terms of the geometric series. So we're just going to use the recursive pattern. If it's a geometric sequence, the recursive formula is to just follow how you get from one term to the next. So we'll formalize that formula in a minute. But to figure out the constant ratio, I need to divide a term by its previous term. So I need to start with 30.25 and divide by 11, and 11 divided by 4. This has to work for every term in the sequence. Well, I'm getting a common ratio of 2.75. which means 4 times that 2.75 is 11, 11 times 2.75 is 30.25, 30.25 times 2.75. I'm supposed to find the next three terms. Well, the next term is actually 83.1875. I'm going to multiply that by 2.75, and I get 228.785625. Then I'm going to multiply that by 2.5, and I get 629.1054688. Now I could have rounded on this one 4 decimal places out, but I didn't do that with the other ones because I was going to be multiplying them to get the next answer. So I wanted to take as many digits as I could keep. But those are the next three terms. And we could find more if we wanted to. Letter B. Now, this one is a little tricky because there are variables involved. So you're looking going, what did they do? Well, we actually have from here to here, something happens that works from here to here. So we're going to do fractions because we've actually been told it's geometric. That helps us. 4r minus 8 over negative 16r plus 32. In factored form, this is 4 by r minus 2, and this would be negative 16 by r minus 2. The r minus 2's cancel. The negative 16th reduces to negative 1/4. Now I need to make sure that that fraction works for the other one too. I already have this factored. I'm going to factor out the 64 from the first term, which gives me r minus 2 as well. Negative 16 over 64 also reduces to negative 1/4. So the value of r is negative 1/4. So all I'm going to do is distribute negative 1/4 into this every time. If I did 64 times negative 1/4, I get the negative 16 times negative 1/4, I get the positive 4. Same thing with the term after it. I have to distribute it to both. So my next three terms, if I have this and distribute negative 1/4, that's going to become negative r plus 8. Then if I distribute negative 1/4, I'm going to get 1/4 r minus 2. Then if I distribute the negative 1/4 to that, I'm going to get negative 1/16 plus 2/4 is 1/2. So there are my next terms based on that being the common ratio. And those were only the next three. We could do more if we needed to, but we are only asked to do the next three, so we're done. The nth term of a geometric sequence can be found using the following rule, the following explicit rule, and we'll talk about the recursive as well. Recursive is easy, right? Recursive, all we have to do is take the previous term, a sub n minus 1, and multiply it by the common ratio. We also have to know what the first value of a sub 1 is in order to use the recursive formula. The explicit formula looks more like an exponential function. So it would be the initial amount, our a sub 1, a sub n equals a sub 1, the initial amount, times our base, which is the common ratio, to the n minus 1. So if I give you the term number, first term, fourth term, fifth term, you just plug it in. As long as you know the common ratio in the first term, you can find whichever one you're looking for. So this is the explicit. Write an explicit formula and a recursive formula for finding the nth term in the sequence. Well, the recursive is the easiest. So for this, I'm going to do 312.5 divided by 25 and 25 divided by 2. Yeah, that is not a geometric sequence. Oh, I put in the wrong numbers. 312.5 divided by 25 and 25 divided by 2. So both times it's 12.5, so we have the value of r is 12.5. So for our recursive formula, given that a sub 1 is 2, a sub n can be obtained by doing 12.5 times a sub n minus 1. Take the previous term, multiply it by 12.5, take the previous term, multiply it by 12.5 to get the next term. Our explicit formula would be a sub n equals 2 times 12.5 to the power of n minus 1. Try this for letter B. In letter B, you should get a common ratio of -2, which means our recursive formula is given that a sub 1 is -1. You can find the next term. You started by doing, -2 times a sub n minus 1. And this is for n is greater than or equal to 2. I should have had that over here as well. N is greater than or equal to 2. For our explicit rule, a sub n equals -1 times -2 to the n minus 1. Now we're going to do some of the same stuff that we did with the 10.2 when we had linear, aka arithmetic equations. And we used the arithmetic explicit rule to find certain terms or specific terms, except now we're going to do the same thing with geometric sequence. Remembering that a geometric sequence is closely related, its explicit rule is an exponential function with an initial amount and a common ratio. So 49 divided by 14 is 7, and 14 divided by 4, or not 7, is 3.5. They're both 3.5, so the common ratio is 3.5. We're not asked to write an explicit rule, but it will help. Since we're going to get the 9th term, since it's only the 9th term, if you wanted to write out your more spaces until you got to the 9th term and just continue the recursive, you could. But it's very easy to do this, especially with geometric, because of the nature of the formula. I just need the first term, the base, and then n minus 1. In this case, I want the 9th term, so 9 minus 1. So I will do 4 by 3.5 to the 8, the power of 8, and I get my answer of 90,075.01563. That's a sub 9. Try this for the next sequence. Be careful though, because notice it's a sub 3, not a sub 1. So in trying this, hopefully you realize that instead of a 1 here, right, in our n minus 1, we can actually treat this as a sub n equals a sub I times r to the n minus I. It's just usually we prefer to have the first term with the first position, position 1, and we're finding the higher term with the nth, with its position right there. So in this particular case, we have 32 equals, well actually I don't even need, if I want to find, I could actually find a sub 1 using 32, but I don't have to. I can actually find a sub 12 by doing the following. 32 times negative 4. Instead of n minus 1, I'm trying to find the 12th position, and this came from the 3rd position. So I have 32 times negative 4 to the 12 minus 3. Giving me the value of negative 8,388,608 for the 12th term. Now, I could have found a sub 1 and then done the formula, and I would still get the same answer, but I don't need to. I just have to use the correct positions. Position 12, position 3. Example 4. Rohan purchased a personal watercraft for $9,000. Assume that by the end of the year, the value depreciates 30%. So that means it was 100%, 1.0, and we're taking away 30%, 0.30. So remaining is going to be 0.70, 70% remaining value, because it lost or depreciated by 30%. So we're supposed to write an explicit formula finding the value of Rohan's watercraft after n years. Well, upon every year it loses 30%. It only retains, instead of remaining, retains 70%, 0.70. So that is our value of r, because from 1 year to the next, we multiply by 0.7 to see what remains, instead of multiplying by 30% and subtracting it from the previous year. Just multiply by the retaining multiplier. So our initial amount was $9,000. So 9,000 is the a sub 1. And our value of r is 0.70, and we put n minus 1. Now when I put this in my calculator, I'm going to put it in the y equals. And what I should do, or what I should see, is that when I put in 1, or actually when I put in 0, it should be worth 9,000, but let's look at this. 9,000 by 0.70 to the x minus 1. Let's take a look at this. We have a little bit of a problem. Here's the problem. When I put 1 in, I get $9,000. That shouldn't make sense, or it doesn't make sense. It doesn't make sense because after the first year, it should have depreciated to 6,300. So our numbers are off. So what this tells me is when I plugged in the 1, something's wrong in my exponent. So I need to come back and revise this. For this particular application problem, my initial value is 9,000, and my rate was 0.70, but it should just be to the power of n. So we're going to see if that works. If I drop the minus 1, it should. That makes sense to me anyhow. So if I drop the minus 1, then that is correct. at 0 years, right as soon as he buys it, it's worth $9,000. The minute he takes it off the lot, it starts depreciating so that a year later, it's worth 30% less, 30% less, 30% less. I didn't have to do all of these, I just wanted to make sure that the pattern looked right to me. And so now I know that A sub 5 is going to be 1,512.60. After 5 years, that $9,000 watercraft he just bought is only worth $1,500 roughly. So do be careful when you're doing your application problems. This is the explicit rule for our series and sequence, but in terms of time, right, and the reason this was off was A sub 1 for us at 9,000 is actually A sub 0. Okay, some of you could have looked at that way. Now, A sub 0 is 9,000. So if you had based your recursive pattern on instead the 6,300, I think it was. Yeah, if you had done the 6,300, then it would have worked. You could have done 6,300 times 0.70 to the n minus 1, because that 6,300 is A sub 1 year later, where the 9,000 is A sub 0. So you have your choice. You can either refine this, revise this like we did when we did our unit on exponential and logarithmic functions, or you can actually find A sub 1 by doing the recursive formula the first time, the 6,300, and then write your rule, and it'll follow the explicit rule for a geometric sequence. I'll leave that choice up to you. For day 1 of 10.3, you are going to be working on page 615, 1 through 30. You get to skip number 9. Have a great day.